In the previous section, we defined the definite integral. And if you recall, the definite integral from a to b of f of x dx was the standard part of the sum of the area of a bunch of infinitesimal rectangles. So remember, this was the height of the rectangle and dx is the width. And these are infinitesimally small rectangles that fit under the curve. And we just add up those areas and adding them up and taking the standard part, we said that that is the definite integral. We worked out some examples in which we use this definition to get approximations. We also worked out at least one example in which we rigorously used the definition where we had a hyperinteger and we worked it out. But as we saw, that method is very difficult, to say the least. This is a great definition. It captures the idea of what we wanted to do by filling the area between the x-axis and the graph with a bunch of infinitesimally small rectangles. However, it may be a good definition that captures the idea of area under the curve. It is a bad definition when we want to actually calculate it. So in this section, we'll develop what is called the fundamental theorem of calculus, which will give us a means of calculating this value without having to go to the infinitesimals. And it'll have to do with antiderivatives and such sort. But before we get there, we have to establish a few theorems and facts about the definite integral. So the first one is the rectangle property of definite integrals. And it says that if f is continuous on the interval a to b, has a minimum value of m and a maximum value of capital M, then we can get a constraint, a bound on this definite integral, that it's going to be no bigger than the product of m times the length of the interval and no smaller than little m times the length of the interval. Now, the proof of this is done quite well in the book, but I'm going to give a pictorial justification for why this might be true. So let us take a look at the graph of some arbitrary function f of x. Then, as we discussed, the integral would be the area under this curve between the x-axis and the value y. So let me shade that region in. And the definite integral would be the area of these two shaded regions. And we discussed previously that it's okay to have this area would be positive, this area would be negative. In fact, just looking at this picture, it looks like our integral itself would be negative. But what we're trying to get at is the rectangle property, that this region, the purple and gray region, which is the integral here, that it would be no bigger than this upper bound, m times b minus a, and no smaller than this region, little m times b minus a. So let's first off graph what big M times b minus a, what that area would look like. So we can see our maximum values up here, and the rectangle, because this is going to be a height of m, big M, and width b minus a. So that's from here to down to here. So a rectangle with that area would look like this. And we see that the red region here is the area of big M times b minus a. And the picture is worth 1,000 words. That definitely the area under this curve is definitely smaller than that total area, since this positive area is fully contained in it and this negative area is below it. So if I take this positive area and subtracted this area, it's definitely going to be smaller than this red region. So we can see that the upper bound makes sense, that the area under the curve is definitely going to be smaller than this red area, big M times b minus a. On the other hand, if we take a look at the lower bound, little m, so that's down here somewhere, that height little m is down here, And if I graphed the rectangle with this area, it would look like this. And we see that this blue region is the rectangle with this given area. Little m is the height down here. That's the minimum value of the function. And the blue area would be little m times the length of this interval. That would be this area. And again, the negative part of the graph is fully contained in this region. So this area has to be smaller than this area. And this area is already positive. So surely this blue area is bigger than the total area. Now the book goes through and does an algebraic explanation for why this is true. But for our purposes, I think a picture is worth 1,000 words. And this is a very handy bound for a definite integral. If we know that it can't be bigger than m, then this integral is going to be smaller than this value here. And if it can't be any smaller than little m, if little m is a minimum value of f, then the integral itself can't be any smaller than this value. So that's a useful constraint. We call it the rectangle property of the definite integral. Now, one fact that becomes very straightforward and useful is the fact that if f of x is positive, so if f of x is always positive, then the integral of, say, a to b f of x dx is also always positive. And this, again, if f is positive, then 0 is a lower bound of f, and 0 times b minus a is still 0. So the integral itself will always be positive. So that's a useful fact. If a function is always positive, its integral is always positive. Similarly, if a function is negative, so less than or equal to 0, so now 0 is an upper bound, this tells us that the integral itself has to be negative. And this corresponds again to if the graph is below the x-axis, if it's negative, then the area is negative, the integral is negative. And if the graph of f is above the x-axis, then the integral is positive, that area is positive. So another very useful fact about integrals is what's called the additive property. And what it says is that if f is continuous, so we need continuity to even define the integral. So if f is continuous and c is any number in this interval, then the integral from a to b of f(x) dx is equal to the sum of these two integrals. So we've got, say, c here and c down here. So what's key is that the upper bound on this left sum corresponds with the lower bound of this integral. And then we've got a and b, which were our original bounds of integration for the left-hand side. So if c is any number in this interval, then we can break up this integral into two pieces, where I've got the integral from a to c of f dx plus the integral from c to b of f dx. And again, the book does a very good job of demonstrating this additive property. It uses the rectangle property to prove it. But again, and here I'm just going to use a general graph to show why this should be true. So here we have the graph of some arbitrary function, y equals f of x. And a is the left endpoint here, and say b is the right endpoint here. And we're going to take c to be some value in between, say here. Then the integral from a to c would be this region here. This is the integral from a to c of f dx. And then this red region would be the integral from c to b f dx. And we should be able to tell quite clearly from the image that, sure enough, if I want to know the integral from a to b, that's the sum of the total, or that's the total area under this curve, then I could break it up into two pieces and compute this integral from a to c, this integral from c to b, and add them together, and I would have the same area. So the additive property just says, look, I can break my bounds of integration into multiple pieces and just add them together. This will be a very useful feature in many applications. And it also is necessary, this theorem is necessary for proving the fundamental theorem. So that's the additive property. So maybe an application with this would be something like, let's say that the integral from 0 to 5 of f of x dx is equal to 7. And the integral from maybe 5 to 10 of f of x with respect to x is equal to -3. Well, then, by the additive property, the integral from 0 to 10 of f of x with respect to x, well, we can split it up. This is equal to the integral from 0 to 5 of f of x dx plus the integral from 5 to 10 of f of x with respect to x. And these values we know, this is equal to 7 minus 3, which is equal to 4. Another application would be, maybe let's look at this one. So the integral maybe from 0 to 8 of f with respect to x is equal to 6, and the integral from 0 to 4 of f of x dx is equal to, say, 3. And maybe we want to know what is the integral from 4 to 8 of f of x with respect to x. Now, here I've got both 0 to 8, 0 to 4. I don't have a common lower to upper, but I can still use this additive property. So I could say, well, this is equal to the integral, so I've got to keep my lower bound, but now I'm going to go up to 0 of f of x with respect to x, and I'll add it to the integral from 0 to 8 of f of x dx. Now, here's something that oftentimes will elude students the first time they see this, that I went from 4 to 8. That's my interval of integration. But I broke it up. I went from 4 to 0. So I'm kind of going backwards, and then 0 to 8. But what's key here is, again, the lower bound of 4 is the lower bound here. The upper bound 8 is the upper bound here. And then between the two, this 0 is the upper bound here and the lower bound there. So as long as I've got the lower bound here and the upper bound of my original function on these two integrals, and that this number is identical to that number, then that's the additive property of integrals. Now, if you recall from the previous section, because I don't know what the integral of 4 to 0 is, I know the integral of 0 to 4, but by changing the bounds of integration, we just introduced a negative sign. So this would be equal to negative 0 to 4 of f with respect to x plus the integral 0 to 8 f of x with respect to x. And these values we know. I know the integral from 0 to 4 of f is 3, and the integral from 0 to 8 of f is 6. And so this would be negative 3 plus 6, which is positive 3. And so those are two kind of straightforward applications of how the additive property is useful. Again, it's very important in the proof of many of these theorems. So in the next video, I will introduce a couple of more ideas before we finally get to the fundamental theorem of calculus.